In progress.
I'll change the view to the presence because these guys come up. Oh,
Right. Content.
yeah. All right. Good afternoon, everyone. I'm Dasun. I've got Abdullah alongside with me. Shiv was going to present as well as one other person, but he's ill and he's lost his voice. So I've added some two emojis to okay, cool. Two emojis to hoping he's well now. Okay, so we are from PSD, which stands for Production Software Development. Sorry, technical challenges. Okay, cool. I don't know why it's not appearing. Okay, cool. So we are from PSD, sorry about that, which stands for Production Software Development. So at PSD, we primarily work on our both short and long read limb systems. Our tech stack is quite polyglot by nature, so it's quite natural for us to explore other avenues in terms of technology tools and obviously programming languages. And this presentation is about our journey in learning a language which was quite new for us. We want to share the triumphs, the challenges we face, and hopefully leave you with some takeaways. And we kindly asked you hold off the questions until the end because we want to give you the key takeaways, and you can obviously ask the questions afterwards if there's going to be time. So for people on Zoom, if you don't get to ask the questions, if the time doesn't permit it, you can send out the questions via Slack or email. I've like highlighted the names or the handles or email handles. Yeah, you could always get in contact with us. So, Ross, it was this shiny little programming language that everybody made their code base and say, hey, you know what? We need to rewrite this in Rust. I mean, this wasn't just us. I mean, this happened in the Linux kernel. It happened with Git's Riff Table. Riff Table is a way of compacting storage in Git refs. It's coming out in Git 3, I believe. But yeah, that happened to us too. But we knew none of our BSD applications would actually need a rewrite. They were just doing fine. But we did figure out that Rust would be a great excuse to explore how programming could be made safer, how it could be written in a more safer way, safe philosophies. When it comes to those, sneaky memory leaks that you read on blog posts, every couple of weeks, CDRs and all that stuff. So we've got Steve in our audience. He's my line manager. So we both started working on a prototype because we thought that doing something was better than just going through a bunch of tutorials and a bunch of like courses and stuff. So and then we found Abdullah and Shiv, who is not here today. So we found kindred spirits in them. So both equally wanted to like explore Rust in a more hands-on, in a collaborative approach. So as I mentioned earlier, so the prototype that I mentioned earlier aligns very closely with our domain. It's essentially a reimagining, oxidation, if you will, that's a pun for Rust, rather than developing a fresh new application. So this application is called Labware. So you can see that there's WHERE, so it's where are my plates and tubes. That's the meaning of it. It's basically a tracking system for plates and tubes. So it does provide two use cases. The first one is scanning in a piece of a plate or tube to a given location. The other one is searching for that plate or tube has been scanned into the proper location. So there are like two use cases that we've taken out of it to build a prototype. The prototype is a backend artifact that we've integrated to our LIMS system, or LIMS frontend, long read LIMS frontend called Traction, to showcase its functionality. The connection to the long read LIMS is controlled via a feature flag. So flipping the feature flag would direct the traffic between the original Labware service, which was written in Ruby on Rails. So it's a backend service which was written on Ruby on Rails, but the prototype was written obviously in Ruby. So the feature flag controls the traffic between traction, and when we enable the feature flag, it will direct the traffic to the prototype. So we need to emphasize the fact that this is a prototype. It was not meant for production. So one of the key takeaways that we wanted to highlight in this presentation is that we've successfully managed to learn a new language, its syntax and the semantics, and used it to write an existing part of a small system and fully integrated it with our infrastructure. We've achieved this through collaborating among ourselves for about an hour and a half per week. And it's been a process we've genuinely enjoyed. So that's the introduction that I'm going to give you. Next, I will give you a demo on what we've actually built. So as I said before, we've hooked the prototype to our long read front end called Traction and enabled it through a feature flag. So Traction communicates with the prototype to scan the plates or tubes and searches for them. So this is the interaction, basically through a sequence diagram. So this is going to be a quick demo, but know that the Labware prototype is the one that's serving up the scanning and searching of the request, not the original Labware service which was written in, on Rails. So this is Traction. I am going to have to copy this and stop sharing for a minute. And another window. There we go. Cool. So this is Traction. So Traction is our long read limbs front end. So we've got a bunch of things that Traction could do, but we wanted to get your attention on scanning in pieces of Labware to particular locations because we wanted to demonstrate what we did with the Rust prototype. So, so these samples that we have here were imported from SequenceGate, which is our short read backend component. So what I'm going to do here is you can see that these are plate barcodes and these are the wells. So what I'm going to do is I'm going to take one of these plates and scan in a particular location that we have in the Rust prototype. So how do we do that? I'm going to copy one of these plate barcodes. So Traction has this this feature called Labware reception, which allows you to give the specify the location that you want to scan your plate or tube on. In this case, it's a plate. And you can give the plate barcode or tube barcode that you want to scan in. So I'm going to paste this in. I need to type my swipe card ID or the user barcode. It's right. And we've got like some predefined locations in the Rust prototype. So this is one. We've got some other stuff as well, but I can't remember any of them. So I'm using this one. So for our demonstration, this should be fine. So what I'm doing here is that I'm scanning this plate into this location, which is supposed to be a freezer. So it says that one Labware, so there's this term again. So Labware and Labware. There are two different things. So the Labware is, this term stands for a piece of plastic. It could either be a plate or a tube. The Labware is, where is the Labware? I know it's very confusing.
Keep saying it, we'll get that.
Yeah, I'll pronounce it. I'll try. I'll stop trying it. Okay, so we've tried this, scanning this into this particular location. If I go to the home page again, and example, well, you can see it here, but it kind of defeats the purpose. I'm going to search it. Pause. As you can see, the filter view. Okay. So it has been scanned in. So it used two endpoints to do this in the Rust prototype. The first one was obviously scanning in, and this view comes up when you send another request, which is another endpoint, which is called the search endpoint. This is the second use case I've talked about. That's the demo. I know it's a quick demo, but this is the prototype was built with, I mean, from scratch with no knowledge with Rust on the background. And we've achieved this. I know this is a web application. I don't think Rust is very, it has use cases for web application, although there are like frameworks like Axum, Rocket, and stuff like that, which gives you out-of-the-box web capabilities. But we've developed this prototype with very small amount of abstractions used. We had to use some abstractions like Hyper that does request response cycle. I know Abdullah will talk about Tokio, the asynchronous runtime. But we've managed to do this with minimal abstractions introduced. So we're kind of proud of that one. So going forward, I am going to share the other view again. It's going to be this, no, this. No, not that. This. Cool.
Yeah. So when we start the project, our goal is to learn the language itself. We could just pick up a framework and use that, but it will not be helpful for us to learn the language, because we will be targeting learning the framework rather than learning the language itself. So but at the same time, we want to reinvent the wheel and then do everything ourselves. For example, we don't want to write a socket server, write a web server, and then to arrange things for our business. So what we did is we made use of a few essential building blocks from the ecosystem. We have three dependencies: Tokio and Hyper and SQLX. Those dependencies are called crates. You use a crate, bring them to your project, and use the functionality of them. It is also word pointing out that we didn't focus on the security aspects in this project because we are working on a prototype to learn the language. For example, access control headers or same origin policies are not concerns for us for this project. And also we enabled even the HTTPS and HTTP mixed content in our browser to show that demo. Yeah, so first thing first is Tokio. Tokio is an asynchronous runtime. Rust itself provides, keywords like async, await. You have things for handling sockets and everything. But the thing is, then we don't want to build everything ourselves. We have Tokio, and this runtime is providing us even with scheduler, timers, IO drivers, everything we need for as a base. And we use Hyper for network protocol handling, HTTP handling. So we reduce it down to handle the request response cycle. So we can focus on that. And we are using SQLX to access the database. We are using that crate as the database driver. The overall architecture. So all starts with the client requested something. So as shown in the demo, controller dispatches it to right service. In this case, we have two services in the service layer. One of them is scan, one of them is search. And we have models to interact with the underlying database. These are data models. They are corresponding to Rust structs, actually. Models. Our controller is simple, a single function, actually. It is responsible for handling the incoming HTTP request and dispatching the request to the right service using the root function. The root function dispatches the request, it receives the HTTP request and decides which service should handle them. The important bit here is the match statement. This is very common in Rust. It is a tool for pattern matching. It might look like switch statement, but it's more powerful than that because it is an expression. It can return a value. It can match anything, not like integers and enum values. A couple of things. Here, in this case, we are matching the incoming request, hyper request, into, we are saying whether this is a post requested scan, and then passing it to the scan function. You might notice that we have awaits there, because we have async calls, we just waited for the result. And in the future, if you deal with Rust, you might remember that in Rust, when you're returning things from a function, you're returning actually a double meaning thing. You're returning a result. It might be a successful result or an error result. You might be handling each of them. The caller's responsibility is to handle them explicitly. Question mark means bubble up the error, shortcut and bubble up the error in this case, in the stack. In a similar case, for the other service searches, we are matching that and then returning it. And if we can't find any match, we are returning the not found result. Switch. These are the service functions. We are passing a database connection pool and the request string. You might notice that the service functions look a little bit different. It is because of our experimentation of the ownership issues. In the first case, what we are doing is we are passing it. The function becomes the new owner of the string, and in the second case, in the scan case, we are passing a reference actually. And one of the things to mention in our learning, which is very important, we always written tests for whenever we write a function, we wrote our test. This is the way we learned. Without it, we couldn't be here. You might see that there's a configuration annotation here that it says to Rust. Does it change now?
Yeah.
You might see that we are defining a test module within the same source unit. It is just next to your code. It is saying that, okay, when you're testing it, compile this section and run it as a test. And in the Tokyo test case, that annotation is showing that, okay, Tokyo start a asynchronous runtime, put this function in and run the test for us. Of course, these requests and responses are thanks to Hyper. I mentioned test. And models, we gave an overview here. We are giving an overview here. Dustin will show a few things later. Models in Rust, we developed them using structs. So the Labware struct, for example, has an ID of unsigned 32-bit integer and a barcode string and a location ID unsigned.
Be seeing the models now.
Yeah, we should be seeing the models. And I can't see that because there's a glare. Yeah, I cannot. Do you see this?
Yes, yes.
Did you see this?
Yeah. Yeah.
No.
Yeah, yeah.
Right, okay.
Yeah.
Actually, yeah, Yeah, sorry. Sorry about that. So I was talking about the love extract. Yeah, I said it. I told about fields of it, an unsigned 32-bit ID and a barcode string, and the location ID to refer to the other place where we are recording it. So when we implement the struct, we are also implementing functions for them. So these functions need to create, update, and those ones on the LabVIEW model side. These are the functions we implemented for that. It looks similar to making it like an object-oriented thing. And it also maps the create, read, update, delete pattern, although we don't have deletes here. Again, the test we wrote is all our experimentation and hammering of the code to get it working and learning about the Rust. That's why we have so many of them. I'm handing it over to Justin for more code information.
Yeah, the dog gives on me to be an icebreaker or anything like that. It's just something I've added to fill up the space. Okay. So I'm gonna go through a bit of the code underneath all the demonstration and what Abdullah said. So the intention is not to like teach Rust. It's just to show you how the code is structured and all the experiments that we've done. All right. Let me share the code. Stuff up on my screen now. Good. So Rust compiles to native artifacts, and Rust has a main function that runs when you run the artifact. So this is the entry point that you see. So as Abdullah said, Rust provides you the asynchronous grammar in its CFG, the grammar that it provides you. So the syntax is there, but it doesn't provide you with an asynchronous runtime. So you need the IO timers, event loops, and all that stuff. So Tokyo is the one that we've chosen to provide that runtime. Abdullah mentioned that. So this is what a typical asynchronous Rust main function looks like. So there are two ways a Rust program could be, or a Rust library or a program could be packaged in, either as a library or either as an executable. So in this case, it's an executable, so it's built as a. So one cool thing that Abdullah mentioned was results and results. So this is like into if you've seen programming language like functional based languages like Haskell. You might have seen something like this as the return value either or structuring thing in Haskell. But what this does is it specifies that the return type of the main function is either a void type. So this is the successful case. If it's an erroneous error, it goes to this type. So basically, it's a result of either a void value when it comes to a successful response or an error of this type. So we can go deep into it, like what box is. A box is basically it's a small pointer that allows you to allocate memory in the heap. Otherwise, by default, Rust allocates memory in the stack. So boxing up is a way to allocate memory in the heap. So all the other stuff, I'm not gonna go through every one of them. These are like basic network programming stuff. You allocate a socket and have a TCP listener listening to incoming connections. But I do want to mention this. So this is one of the abstractions that we have used. I told you before that we've used an abstraction for serializing the request and response cycle. So this is Hyper's way of serializing. Let me see. No, it doesn't give you a. So this is a Hyper. So it says create a service from function. So basically what service function does, it accepts a closure. Closure is an anonymous function like a lambda. So it's one of those things in Rust that you might have called, you might have heard the phrase zero cost abstractions. Zero cost abstraction is basically a way of declaring abstractions without any cost. This is one of them. So request object or the value here or the struct here is provided by Hyper for us to work with. So we've written a process function, which is basically a controller in other frameworks that you've seen like Spring or Rails or something like that. So Abdullah talked about this function. So this is the heart of the controller root function. So you've seen this before. It's basically dispatches service to dispatches the incoming request to corresponding responses. So this is what a service looks like. I don't really want to explain a lot of it, but I want to show you the flow, how it goes from one end to the other. So if you go create, which is part of the model where you find the SQL queries. So you can see find by barcode, create, all these are raw queries, well, parameterized raw queries. All these things are parameterized using binds. And when it's done, it's propagating the result upwards like this. So if the result is an okay, it will prepare the response. This is where Abdullah said we've kind of forgotten about security. We've synthesized a hyper response and bubble it up. If it's an error response, we've obviously preparing error response and bubbling it up the stack to the call the main function. So basically that's what the main function does. It's a very simple function, but there's a lot of experimenting going on in here. So you might find we are passing values. So we are passing values, just raw value without references, which is not really ideal. We've kept it as it is. We can optimize it and modify it, but we didn't do that. But we kept it like as a snapshot of our learnings. If you are doing a production-ready development, we're obviously going to change that. But yeah, this is a working process that we have. In terms of deployment, let's share the screen. So in terms of the deployment, so I told you that Rust builds into a native artifact. So we've built it to a native artifact and created an OpenStack VM. So at PSD, we provision our own infrastructure through Terraform and Ansible as IAC, infrastructure as code. So we've created the OpenStack instance, deployed it there, deployed the prototype there, and we've got a network that Traction is in. We've bound that network to the prototype so that Traction could communicate with the prototype itself. So the network architecture and the compute architecture are all there. So that's about how the application was built and how it was developed. And about the future of our journey in Rust. Let me quickly show you one thing. So So we've chosen this this new tool called OXC. It is a suite of JavaScript library, JavaScript executables, not libraries. So it's meant to be as an oxidized version of ESLint. So ESLint is the linter of ECMAScript based files. So they are developing this this new linter called OXC. It's got a different components, but what we are usually trying to contribute to is OXC. It's to OXC. So what we have done is ESLint has got multiple rules, like for example, no debugger rule. If you put a debugger there and you run the linter, it would just complain that there's a lint, there's a linting error, there's a debugger statement. So this is the Rust version of that. So we've chosen a rule called no warning comments rule, and we are implementing that. This is an open source project, so it goes through the open source pipeline. You choose a rule, you create a PR, and you get approved, you get a discussions, and it's all merged in. It all gets to merge in if all the test paths, there are benchmarks. So we are still working on that one. So we think that we are trying to apply the fundamental concepts that we learned from the prototype. So that's basically the future that we think that we are going to go on Rust. Abdullah, do you want to put this somewhere?
So we are now talking about what we like and what we don't like about it. In our experience, we see now. Things we liked. Okay, we liked pattern matching with match statements. It is really powerful and you can match anything. And we like the explicit nature of it. You need to handle, although we didn't always implement it, we unwrapped it or just bubbled up in the stack, but we liked how it went. In the, for example, handling the result with okay result and error result, or I'll talk about the other one in a moment. We like the functional style enums. This option means you either get something out of it or you get nothing. So you don't have null pointer errors in this language. So you have a null value. If something is returning a null, then you have an option then. You can't have something, you are claiming that's an integer, but it's not, there's no such thing. And the result, yeah, we mentioned this earlier, but it's an okay result or an error result you need to handle. We like that. And the cargo as the package manager, it is very powerful in terms of tooling. You can build, just create a new project and then build it and then build it, test it, format it. Everything is in that command. It's very useful. And it is a very good package manager. You have a configuration file, you define your packages you need, and then it creates a log file, it freezes that, you can reuse it, and it's reliable. And another good thing about Rust is it is backward compatible all the time. In the configuration file, you just specify which edition you're using it, and that's as package manager, we were very happy about Cargo. It made our life very easy. We just did cargo tests, we just did cargo format, everything. Yeah, we like it. Things we like, but okay, found difficult to grasp. It is not only us, everyone finds these things difficult. The borrow checkers, every value must be owned by one thing. It can't be owned by several others. You need to be very explicit about it. You can borrow it, and even when you have rules, for example, you can borrow it as mutable. If you're doing that, someone else cannot borrow it immutable. You can't mix and match those things. There are rules around that. This is the main bit. When they talk about steep learning curve, this is the main bit they are talking about. And lifetimes are, yeah, it is related to borrow checker as well. For example, your function is returning a reference to a value, then you need to explicitly specify the lifetime of it in the function signature, saying that, okay, this reference lives as long as these parameters. You can't just arbitrarily return references to things. This is mainly about avoiding dangling pointers or pointing to some free address. The Rust's main point is it is very sensitive about this ownership ownership concept. And the boxed values, again, this is related to ownership. In this case, these are heap allocated structures. The box can be owned by one thing, shared. It cannot be shared. Yeah, I'm just trying to remember. Okay, the arc one. Okay, box cannot be shared with multiple threads, for example. We have a very sensitive issue here. So in sometimes you're programming in a language and you're saying, oh, okay, I promise I'm putting it in multiple threads, this value, but I promise we will not modify it. There is no such thing, okay? You need to explicitly, in this language, if something is shared, you need to know it, and the compiler needs to know it, because there is no garbage collector in language, and everything needs to be known beforehand, and compile time, it needs to know that it's safe to do so. And ARC can be shared with multiple threads. Yeah, actually, you can compare box to unique PTR of C++. arc to shared PTR of C++ smart pointers. Some analogy. Things we didn't like. Yeah, we liked the result and option, but we didn't like writing too long code and then saying that, okay, if the success is, we think that it's always returning some value. Sometimes, okay, it's always returning some value. You don't want to handle the error. We just unwrap it. Of course, when you unwrap it, and if there is a null return there, then it will be panicking, of course. So we were lazy. We used unwraps, but we were developing, and it's not a production ready code. So yeah. And slow builds, if we are used to interpreted language, there is no compilation step, but we were really not patient enough waiting for compiling something. So it is a slow build. Compilation takes time. And especially when we were dealing with ESLint, we were just compiling the whole project. It just keeps going and going. But yeah, it's not something you do every day. Actually, this is not our everyday language, so we complain about that. And the other one is, it has sometimes cryptic looking messages when you're compiling things. And this one, it's trying to say actually, okay, I know there is a function trait defined here, there's an interface is happening, but I don't know where this implementation is coming from. That means that, for example, the answer to this error would be putting use statement at the top of the code to say that, okay, this function is coming from here. So it is very sensitive about where things are coming from, who owns things, who references things, how long this value will live. These are the important bits in the language. Yeah. Right. What else? Okay, useful links. We provided in this presentation, these are clickable links to Rust OXC project. We talked about oxidation, OXC. And we talked about Tokyo Hyper X. These are the links to that. And link to our code is there as well. And this presentation is available online. And this is funny. Yeah, there's a Rust developer. We find this video very funny. We wanted to share that with you as well. You're not clicking now, but yeah. I think I just handed it over to this one now.
Oh, sorry. Right. So Abdullah did mention about the things that we liked, things that we didn't like. So we've actually come to the end of the presentation now. So what we wanted to share now is basically the key takeaways that we have that we kind of wanted to for you guys to take home with. Oh, I've not shared the screen. Share it. So the first one is about collaborative learning. So it was essentially the key that helped us to reach this milestone together, because I don't think I would have been able to do it, because this was like an hour or maybe hour and a half per week. So collaborative learning was really helpful in terms of getting the momentum going. And the second one is about effort. By putting like small efforts, consistent weekly efforts, we were able to make steady progress, small but steady progress. The third one is about abstractions, keeping our approach minimal and light on abstractions helped us better to understand the core philosophies behind behind Rust. And finally, through it all, learning together kept our motivations high, eventually inspiring us to contribute to open source projects like OXC. So we hope that you've taken something out of the presentation. So the presentation was not about the technicality of the language itself, but it was essentially about for us being able to learn a new language and develop something and inspire us to work on something else by collaboratively learning something that kept the momentum going. That was probably the biggest takeaway from the journey. Yeah, that's the end of the slide. If you have any questions, we are happy to answer them.
What do you mean by keeping abstractions to a minimum?
So I know we've used some abstractions. Like we didn't use something like Rocket, for example, a full-blown web framework. We didn't use that.
Oh, okay,
That
yeah,
was
so
what
you
I mean
mean,
by abstractions.
I know you said about the things you liked, but was there anything niche, like saying, "Oh, I like this specific keyword," or something really silly? Is there any niche you'd liked about it?
Question mark was quite niche. Have you seen it in any other language? Question marks, like bubbling up the errors.
Marks.
so with those question marks that you left in, would they be a problem in a production?
They will,
Because if something went wrong on that route, then the whole application would exit.
they will be handled by the main function, which you shouldn't do. They'll panic. Yeah, that's a problem. That's a problem in production.
I don't like lifetime syntax, single apostrophe or symbols and scripted. I really don't like it.
I really like the fact that it was functional and not OO, and I really liked structs and enums. Enums in Rust are really quite powerful, especially when you use them in match statements. I've never seen anything quite like that, and I wish there were other languages that use those.
Well, there are other quite niche stuff if we want to talk about niche stuff. For example, if people say that Rust is quite safe, well, it is. If you, so I am, so I'm doing this course called Performance of Web Programming. So one of the exercises is to create an 8086 instruction decoder. So you got a huge binary file with 16-bit instructions. You need to convert it back to assembly. So one of the things that I've seen is that if you want to like use many intrinsic types, for example, if you want to call a CFFI a foreign function interface or something like that, there are unsafe operations. You basically can't call the APIs through Rust FFI without using unsafe. So in Rust, if you are, for example, say that you have a pointer, right? Like C, like pointer. It might be easy for you to show you. Hang on, let me share the entire thing. I will share the entire thing. Yes. So,
Then I guess there are lots of C libraries like the SQLite library you use that have got nice Rust wrapping that you can
yeah,
use.
they're handled inside. Yeah. Let me just, I don't know, stuff like this.
I have a question is, why is your lines, what's it called, your line numbers, that like when you're in the middle of a line, it says how many back or up or
Yeah, it's relative numbering.
yeah.
Yeah,
I've
it
never-
helps in NeoVim to jump up. So if you want to like jump 5 lines up, you just press 5J.
Okay.
Okay,
I've
sorry.
seen that, to be fair.
Yeah, it's a new way I'm trying.
You don't have to count.
Yeah, well, it makes sense, but yeah.
Well, anyway, so one of the things that I want to show you that people are saying always, Rust is safe and all. Let me show you an unsafe example. This is something that I've learned through that course. So let's say that, like in C, right? Have you got? Do you know about pointers and stuff in C? So in C, let's say I create something like index, I don't know, something like 5, and I try to create a pointer to that int, maybe like an address of X. And if I want to like print it, that's wrong, printf, I'm gonna use D, and then, new line or something like that, and dereference it. So this is C's way of dereferencing a pointer. This works in C. So what if I want to do something same in Rust? What I mean by is, what if I want to use pointers in Rust? That is possible. You can do that. It's fairly easy, in fact. So if you get let X, I'm gonna do the same thing I did in C, but I'm gonna decorate it. So in C, I think the default type is signed integers. So I'm gonna use 32-bit signed integers, go to the 5. And I'm gonna create a pointer out of it, which is the second step that I've done in C. So I'm gonna name it B, because this is constant pointer. I'm gonna constant it. Constant I32 should be I32. This is the type of the pointer. And I'm gonna give a row pointer const of X. So this is the way that you create a pointer in Rust. So let's see what happens when we try to print it. So to print it, you need to dereference it through the pointer. You can print the value, of course, but it's just an exercise to show you how Rust can be out there. So println is the Rust macro. If you guys go through one of those, there's a Rust book if you want to go. If you guys want to go through, it's really. You can go through Rust syntax and macros. So what I'm gonna do is do the same dereferencing. This is my LSB. It's kind of I just wanted to make this kind of a surprise, but it's not allowed me to do it. It's telling you what the problem is. So can I zoom in now? Okay, so what the problem is that it says that dereference of a row pointer is unsafe and requires an unsafe block. So we can fix this. So Rust deems that this operation, dereferencing operation, is an unsafe operation. So you can get rid of it if you want to through an unsafe operator. So what you do, and then, well, it solves the problem. If I want to compile it and run it, I can just go to terminal, cargo run, yeah. Or I can build and run it. I just can run it and it will work. Sorry, the wrong project, sandbox. There you go, fine. It will all well and done. But why did it complain? What is Rust's problem with dereferencing? So to check this out, let's just modify this code a little bit so that we could understand what's going wrong with it, what could potentially go wrong. So if I like do something like this, not the same C program, but let's declare pointer, right? But in this case, let's declare it as mutable. Just for the sake of it, I'm gonna keep the same pointer type, but it's gonna be a mutable pointer type. And I'm gonna create a block. I will explain what this block is. Again, I'm thinking this example in my mind. I'm gonna keep this block as it is. There's a fundamental philosophy behind the block in Rust. I'll explain that. And I'm going to declare an X value, which is an I32. Well, Rust has got, so if you declare local variable like this, it will infer the type for you. By default, it's going to be I32. I myself like to declare these like that. I think it's a personal preference. What I'm going to do is I'm going to assign this pointer. I'm going to assign. So we've forward declare the pointer, and I'm going to assign this the value of this. Sorry, a pointer to this value as B. Right. So I'm going to give mute. Right. Yeah, you need to mute it. You know, make it. Oh.
It's X that needs to be mutable, not a point.
Oh, right, sorry, yeah, thank you. Yeah. Okay, so let's try printing. Oh, no, that's not good. So this is kind of a similar for, so we can't do this, we can't do this, so we saw that, so we need to move this into an unsafe block. Let's move it to an unsafe block. All right. So there's no compile errors. There's no issues with it. Let's try to run it. Works just fine. But the fundamental theory behind the ownership system in Rust, Abdul explained it, is that any function or any block, any variable that you declare within a block or a function, well, function is technically a block, is owned by that function itself, that block itself. So when this block pops out of the stack, theoretically, these values goes out of the stack. So this pointer, the value that this pointer pointed is not there anymore, theoretically. This is, if you're into compiler design and stuff, this is a very common problem. This is called dangling pointer. This is why garbage collector languages don't have pointers like Java and stuff, because the garbage collector could get rid of the memory and the pointer could be still hanging in. So this is dangling pointer. This value does not exist. But why did it compile? So I was like thinking about this quite a while to get this realized. But the thing with this is when you pop this out of the stack, Rust doesn't necessarily clean out the memory. It just resets the stack pointer. It just doesn't get rid of the memory. But what could get rid of the memory is when you are working on a very highly constrained environment where memory is very, very restricted. In that case, if you declare something like int y equals 15 or just the same thing, I32, that's C, it's wrong, let. So if you do that, if your memory block is a very small piece of contiguous block, that's a problem, because there's no way that this could be allocated without removing this. So if that happened, this is a dangling pointer. This is, well, it points to something else, not the one that we expected. So it's to get rid of these problems that the referencing has been made unsafe. There are other cases as well, calling C functions through FFI. There's one other thing, mutating static mutable variables, which are in global scope. You can't do that through unsafe. I'm not sure if this is in the documentation, but that one is in the documentation. So row pointers is obviously a clear choice for unsafe operations. But from what I've seen, a lot of embedded code, like the ones that, for example, if you're writing something to an IoT device or something, they use a lot of these unsafe operations because they need to interact with C APIs. Yeah, so people say that this is, Rust is very safe, but it could be made unsafe if you know how to make it unsafe. You shouldn't do. Yeah, so this is something that probably if you are developing for integrated environments, probably something that you need to be aware of. Yeah.
Nice, thank you.
Thank you. Thank you very much.
Right. So we stop the recording.
Yeah.
Thank you, everyone on Zoom. Unfortunately, you can't unless you're right. Oh, hold on. Tom Whiteley is raised.
Still recording.
Oh, there are.
To ask a question.
Yep. Let's we answer the questions now.
I think that might have been an accident.
Oh,
Might be.
So, was Tom asking a question?
I think he was just saying that he wasn't asking a question.
Okay. So, if you're available, we can on IDS's credit card, we can go and have a drink at the diner for a few minutes.
You've got access to IDS's credit card.
Virtual access.
I'm in IDS, so
I don't have access to the actual gold plated credit card, but I'm someone that will sign